Okay, so let's start for today. Let me show my screen. Yeah. So today, this is the 10th week going on, and today's topic is going to be generative models. So first we'll go through what are known as discriminative models. Then we'll go through, what are generative models, and then some topics like generative adversarial networks and variational autoencoders and so on. So yeah. So let's start up front. So what is a discriminative model? So discriminative models are basically those that we have seen till now, where you have been given an input data like this, some D comprising of this data and labels. So x1, y1, x2, y2 and so on. And the task is as usual to predict y, right? We have to predict the label given the um, you know given this x, right? So that is what is a in a nutshell, that is what is discriminative modeling, right? So what we need to do here is we need to learn a model which takes this input x, all the x's that you see in the training data, and it learns an approximate function which is able to then predict or output this particular y, this label or whatever. This y is being output by the model. So that is what a discriminative model stands for, right? And so the task is naturally, so as we have seen in previous classes, what is the task? The task is to learn a hyperplane between different y's like this, right? So you have different y's over here, red and green, and you want to learn a hyperplane that is separating these two y's so that when a new x test, when a new sample comes in, you run it through your model and you predict its y, and you see whether it's lying on this side or this side. Based on that, you find you give an appropriate label to that test y, right? So this is what is discriminative models, and this is what we have seen so far, right? Now, what are generative models? So again, before going into maths and all, what is the purpose of learning these things? So for example, generative adversarial networks, variational autoencoders that we are going through in this week through all the lectures, the main idea is that you try to, so you have been given these data points x1 x2 to xn, right? And now, so these are kind of like, samples from a certain distribution. Okay, these are some finite number of samples from a certain distribution, and we do not know that distribution. But what we want to do is we want to generate new samples from this distribution, from this unknown distribution, by somehow approximating it through a model, right? So again, what do we want to do? We have been given samples like this from a certain unknown data distribution, and what do we want to do? We want to given these samples, we want to generate new samples that are similar to these but not equal to these or exactly same as these. Okay, so that is the goal of generative adversarial networks, variational autoencoders and all those things. And you'll see that also another major thing is that there is no y, there is no role of y here, right? So everything that we are doing, we are doing in the space of data, in the space of the underlying data distribution, right? So just to formally go through what generative models are. So given data D like this, model the underlying data distribution P of X. Okay. So understand that when we are given a training data, it's not that we are given the entire data population. It's just like as if you have been given some finite, some n number of samples from some underlying distribution. And now in order to generate new samples from this distribution, we have to understand what the data distribution is. But since we are only given these few samples, we do not know what the actual data distribution is. That is why we need to approximate it. So neural networks are all about approximating functions, right? So similarly, we need to learn an approximate distribution that is kind of similar to the data distribution, and we need to learn them from this many samples. So that is the idea. And once you are able to learn such an approximate data distribution, approximate to your original data distribution, now you can freely sample more data from it, and that data will be very similar to your these input images, right? So this is your functionality. So what you want is, you are given a true, you have a, there's a true data distribution somewhere out there, right, which we do not know much about, and we have a parameterized model. We have a parameterized model which is parameterized by theta, and what we want is, we want to get that theta, that particular theta, which minimizes the distance between your approximate distribution and the true distribution, given that we do not know the true distribution. So we'll see different architectures do this in different ways, but the idea is similar, that we do not know what the data distribution is, so we want to approximate that through this p theta, which is parameterized by theta. And once we are able to do that, we'll be free to sample new data from there. So that is the idea behind generative models, right? So some questions that might clear your concepts a little bit more. So, like for example, let's go through this. Let's yeah, let's okay. This is a bit too much. Yeah, right. So the question is, in generative modeling, if one okay, in generative modeling, if one chooses to use scale divergence to minimize the distance between the unknown true distribution p and the approximating distribution q theta, so the true distribution in this particular question is denoted as p, which is unknown as written here, and the approximate one which we are trying to learn is given by this q theta, which is parameterized by theta. Now the problem of learning the true distribution simplifies to what? Okay, and these are the options. So in this particular slide, what we saw is that, what we are trying to do, we are trying to find theta such that the distance between these two probability distributions are minimized. Okay, and probability distributions are a little bit different from other vectors. So these are distributions, these are not really the errors to the way to compare two distributions will be different from what you have seen till now, and it's basically achieved through some loss from some distance matrix, like the KL divergence distance, there's J's divergence, and so on. So these matrix are basically there to measure the distance, how different two probability distributions are. So keep that in mind. So in future, if you need to compare two distributions in this way, use these kind of distances, right? And this is a measure which ensures that your um, um, the more these two distributions are similar, the lower this value is. So what we want, our idea is that, what we want to achieve is that we want to learn this p theta such that it is very close to this pd, right? So that is why what we want to achieve through this particular scale divergence is to minimize this. So if we minimize the scale divergence, the theta that we obtain from there, that will ensure that this p theta is very close to this pd, right? And now, so given this formulation, let us expand it. So there's a little bit of error in this formula. So this is given by expectation of x generated from the data, from the samples that you have, and there'll be, I think, this either this pd or this p theta will be outside also here. Anyway, that's not very important, you can look at that later. Probably this pd will be outside also. So this is the pd of x times log of pd of x by p theta of x. That is the formula of scale divergence laws. That is how it's designed. So now let's expand this a little bit more. So expect this becomes, if you break the log, this becomes log of pd of x minus log of p theta of x. And since expectation is linear, you can break this expression in this way. So it becomes expectation of x sampled from the training data that you have. And because, so here also, if you see your data distribution is not known to you, so what you can do at this point is, you have been given some n samples, just do the expectation over those n samples. So this is how we approximate this expectation. So this becomes log of p data of x minus again expectation log of p theta of x. Okay. And now what? So we want to minimize this with respect to the theta, right? And the first expression doesn't contain any theta in it. So we simply ignore this, right? Because this doesn't contribute to our minimization problem at all. So we just keep this one. Okay. So so if you again, so what, so this is how it is minimized. This particular KL divergence expression is minimized in this way, ignoring the first term. So now if you rewrite it again a little bit, so what you want to achieve is the minimum with respect to minimum theta uh, with respect to this expression. Okay, so this minus has gone inside in this particular line, which is fine because expectation it's allowed to do so, right? So it's min of theta, mean with respect to theta of e of x sampled from data log minus log of p theta of x, right? So you are minimizing a negative quantity, right? Which essentially means you are maximizing the positive quantity, right? So this is basically if you so this basically translates to your maximum likelihood estimation. This formula, if you take this negative out, convert this to maximum, then it becomes maximum likelihood estimation. So that is why this particular option is chosen and not the other one. So you can see that these two are obviously not there. So yeah, so minimizing mean squared error and minimizing triplet loss, they are all obviously not true. So yeah, this is how you minimize the, so you maximize the maximum likelihood estimate.
Then how did the first term disappear? I mean, why did we take it off?
Yeah, so here see that we are doing the minimization with respect to theta. Now do you see any theta here in the first term?
Okay, got it.
That's why you just don't take it into consideration. I mean, what I'm trying to say is that this doesn't matter in our calculation, so that is why we don't take it at all. Right.
Yeah, it's like differentiation, right? Okay.
Yeah. Okay. So, given an input x and an output y, which of the following is the quantity of interest in discriminative modeling? So, since I have already talked about this in like 5 minutes ago, I want you to answer this. Oh, obviously the answer is written here. So, sorry about that. But yeah, can anyone explain why this is the correct answer? Why in discriminative modeling? I mean, this is the correct answer for this question. Okay, so this is because, as I said, in discriminative modeling, if we go back again to the top, what we are trying to do is we are trying to predict this y. We are trying to model p of y given x, right? So that is already there in the definition of discriminative models. So that is why very clearly this answer is true when it comes to discriminative modeling, right? So yeah. This is the fun part. So generative adversarial networks, while they are very difficult to train and all, the story behind it is very interesting. And so it's interesting to know that the author of this generative adversarial networks actually thought of this in probably one evening. But yeah, you'll see that this is actually quite fun. So this generative adversarial network is like a two-person game. Okay, so that is why this word adversarial is there. Adversary means, so you, it's as if you have an opponent. Okay, so what is going on is that you have a model. Okay, what you want to do, as I said, in generative modeling, what you want to do is you want to approximate your data distribution and generate samples from there which are similar to your original training data, right? So that is, with that objective in mind, let's look at this particular image. So what it's here, what it says is that there's a bank, okay, and bank contains some real money, right? And there's some thief who is trying to create fake currencies, fake notes, okay, and maybe it's putting those notes into the bank or something like that, okay. So now Um, discriminator is kind of like the police. Discriminator is kind of like the police. Now, given two notes of the same, I mean, they look very similar, but given this real and fake note, the police has to understand what is the real one and what is the fake one. Okay, so that is the police, the job of the cop to understand which one is real out of these two. What is if you are the thief, then and consider this that in our case, while discriminators work is definitely to be the good guy and identify the real ones, we are actually on side of the generator because we want to generate new images. Okay, so if you want to be a good thief, what would you do? Your foremost most important action would be to create such currencies, such notes which look so realistic in nature that you cannot differentiate between this real and fake at all. The police cannot, right? So the generator will keep on trying to create uh, notes which are looking very very similar to the real ones, so that the discriminator is fooled, right? And so that at one point of time, what will happen is that these two look so similar that the police won't be able to differentiate at all between these two. That is what the generator wants to happen. Discriminator would like to, I mean, like the, I mean, the discriminator would want the opposite to happen. They would like to gain the expertise such that in any case they can differentiate between these two currencies, these two, the real ones from the fake ones. So given this bank robbery sort of idea, GANs are also pretty similar. So GAN has what? There's a generator. Remember it as the thief who is trying to create the fake and fake currencies and make it very very realistic. And there's the police. There's the cop who is trying to catch that thief. Okay, and to catch that thief, the cop has to know what is real and what is fake. Okay, so the generator is kind of a neural network which takes some latent hidden input into consideration. So we'll talk about this later. But suppose this is a neural network which takes some input and it's trying to generate some image which is definitely not part of the training set. So this is, we can think of it as a fake image, right? And now what is happening is the discriminator has access to all the real images plus the fake images, right? And what its job is to, this is a neural network as well which is trying to do a binary classification. So given an image like this, it can either predict 1, which means it thinks that the image is real, or 0, which means the model thinks that the discriminator thinks that the image is fake, right? So what would the discriminator want? Discriminator would want to separate these two very well. So it would like to distinguish between these fake and real images very well. What would the generator want? And also what would we want? We would want the generator to generate images. So it will start generating some, when in the start of the training, it will be like it generates very very haphazard images such that it becomes very easy for the discriminator to understand what are fake and what are real. But as the training progresses, we want our generator to be so perfect. It should generate such good images, such perfect images, that this starts to get confused. Okay, so the discriminator at one point of time, after training for some epochs, it will start to get confused that what are the whether the fake images are real or not, right? And it will go up to a point where it can't distinguish between these two anymore. So the discriminator will always output something close to zero point 0.5. Zero point 0.5 means what? That neither it just cannot identify whether it's a fake or a real. So that is our goal for the this is how the GAN network is. The training objective, while it looks a bit difficult, so uh, there are two parts to it. So in the model also there are two parts, this generator and the discriminator, right? And you need to train both of these. So in order for the generator to generate real good images, you have to make the discriminator strong as well, right? You cannot ignore it. So you have to train both of these very very well so that at one point of time generator starts generating good images. So let's break this expression a little bit and think of it from the point of view of the discriminator first. Okay, so suppose you are the discriminator. So what would you want when you see a real image? You would want to output something close to 1. When you see a fake image, you want to output something close to 0, right? So keeping that in mind, what you want to do is, suppose you you sample some image from the training data, right? So training data images are always real. So what are we talking of? What do we take as fake images? They are just the ones that you are generating as new images, right? So take the old training images which are considered to be real, right? And so you as the discriminator would want the output of the discriminator to be as high as possible for the real image. So remember that real is 1, fake is 0, right? So, and d of x is basically given x, any image x as input, d of x is the output of, probability between 0 and 1. So for the real image, this value should be as high as possible. So you can see that we are maximizing with respect to d, this particular expression, which is fine. So we are trying to maximize this particular output value, which is coming from the discriminator. Secondly, you should also want the opposite. So when you are getting the fake images, you should not want them to you should want your discriminator to output something very very close to 0. Okay, so it's basically its output should be minimized. The value that this particular d outputs, that should be minimized. That is given by this. So any uh, fake image that you are generating through the generator, so this that is given by this g of z. So g of z gives you the generated image, which is the kind of a fake image, right? And by doing this 1 minus d, what you are ensuring, you are doing this 1 minus d and you are maximizing. Okay, so when will this maximize? When this d of g of z is as low as possible. So right. So that is how you are trying to achieve this. So you are maximizing with respect to the discriminator. The idea is very simple, that you want for the real images, you want your output to be as high as possible. For the fake images, want your output to be as low as possible. Right. So now think of the point of view of the generator. For the generator only has one goal. It will it will generate images, and those images, so the d should be fooled by those images. So the d should think that those images are real, which means it should generate something close to 1. It should output something close to 1 when it gets those generated images. So that is achieved by this. So if you uh, kind of minimize this quantity, that that goal is achieved, that you are encouraging, you are teaching, or you are making the generator learn in such a way that it's forcing the discriminator to output something which is very close to 1, which means that the D is thinking that even though the actual image is fake, it's thinking that the image is real. So that is how the training objective looks like for GANs. So it's like, so always if you want to think of GANs, always remember this image. So everybody does that nowadays. That just remember this to be a game between this generator and discriminator. So it's like a police thief sort of game and competition, where ultimately you would want the thief to win because you are trying to generate good images, right? So generally, what they this is another loss function that is used by GANs. So they try to generate so this P of G is basically the probability distribution of your generator. You would want this to be very very close to your true data distribution. Okay, and that is, as I some while ago I mentioned this J's divergence loss. So that is nothing but a fancy version of the KL divergence loss, where You take the scale of PD and PG and KL of PG and PD. So if you go back and look at the formula of KL divergence, you'll see that they are not commutative. So you cannot, so inverting these two don't result in the same value. So you take this in terms of both, I mean in both directions, D first, G later, and then G first, D later, and you just do an average. So that is also another loss that people use in order to, so that this generator's distribution becomes as similar to P of data as possible. So note that this is what we were trying to achieve from before, from the beginning, that we were trying to, you know, approximate this data distribution in some form, and that is given by this particular loss function. Now, when it comes to inference time, so inference happens when once you have trained the model, which also means that once you're, I mean, when does the training complete? When you as the generator, you have almost fooled the discriminator. So you have almost fooled the police, and you are now able to generate fake images in such a way that the police cannot even identify uh, or distinguish the fake from the real. Right? So at that point of time, your training stops, and now that because you now have a good enough generator which generates such realistic images that the discriminator cannot even distinguish them from the real ones, when you do inference, you only need the generator. Okay, so you again sample Z from some Gaussian noise. So that is how the generator is designed to work. So you did give this noise as input, and then your this generator image generates some image, and that is supposed, because now the generator is trained well, it is supposed to give images that are realistic in nature, right? So So these are GANs in very short, and there are lots and lots of variations of GANs. So GANs came out, if I remember correctly, in 2014, but still there's a lot of ongoing research even after 8 years. And if you go back, you'll see that there are so many GANs available now. Uh, GANs for faces, GANs for scenes. So all different kind of GANs with different powers are available out there, and there's a lot of research going on in that direction. So yeah, go ahead and have a look at the interesting papers that are out there. So, but all of them share this basic principle that I talked about. So this generator discriminator, mostly this same principle is shared by all the variants of GAN. So uh, maybe based on the problem that the people are trying to handle, they have added some other functionalities, but the basic architecture is still the same. So there is another architecture called variational autoencoder. So note that here again, for all of these generative models, there's no role of Y. There's only X. Okay. And variational autoencoders are also another form of, you know, another form of generative models which are used to generate images. Okay. So they are also pretty interesting, but yeah, firstly, how did variational autoencoders come into existence? So they are a variant of what are known as autoencoders, just autoencoders. Okay. So the autoencoders, how were they created? So you'll see some explanation, good explanation in this thing also, the code that I'm going to show you today. But yeah, autoencoders, why they came into existence? So images, if you see, suppose 224 cross 224 cross 3. So that's a huge number. So that's a, if you flatten it into an array, it's a very high dimensional array, right? So now it has been seen that if you if you kind of, I mean, the entire this so many dimensional array is not required, right? You can approximate the information that is there in the image into a much smaller vector space, right? Or much smaller feature space. So that was the idea behind autoencoders, that from an image you have to, just given the image, you learn some feature from that image, such that that feature more or less summarizes that image. Okay, so the idea was this, that given an X, so I'm going to explain autoencoders in this image only, but I guess it won't be that difficult to understand. So given an image X, you have an encoder network which will map this X to some latent feature Z. Okay, forget about these mu sigma values for now. Just imagine that given this X, you get a new vector space, new feature space Z, which is of a much smaller dimension than what X was. And then given this particular Z, uh, what you are trying to do is you also have a decoder like this. Okay, so this takes Z as the input and it tries to generate the same image back. Okay, so that was what the function of autoencoders was, that your features should be such, so you want to learn some latent feature for a given input X such that from the feature you can reconstruct the image back. That was autoencoders. So what is variational autoencoders? So they are very similar to autoencoders, uh, just that they have some extra assumptions. So they have put some restrictions on the latent dimension Z. So autoencoders, you see, what they do is they take an image and through a neural network they plainly learn some other dimension Z. I mean some other feature vector Z, which is smaller than X. But there is no restriction on what Z can be. So suppose Z is a 128 dimensional vector. So in that 128 dimensional vector space, it can comprise of anything, right? Here, variational people say that no, we'll restrict Z in such a way that Z can only be Gaussian in nature. Okay, so yeah, it can only be sampled from a Gaussian distribution. Okay, so there are several benefits of using it as a looking at it from the Gaussian point of view. So what they're trying to do is now that since you only have to, you know that from your prior assumption or knowledge, you know that Z is going to be sampled from a Gaussian. Now you do not need to explicitly, uh, you know, compute Z from the encoder. All you have to do is take an image X. There's this encoder neural network. You just generate the mean and the covariance matrix of the Gaussian. Okay, so that will be enough. So because you have assumed that this Z is part of a Gaussian, right? So all you need to do is take this. I mean, learn this mean and the sample and the covariance matrix. So that will now that you know that, all you have to do is, in order to get the Z, you need to sample from this normal distribution with the same mean and the covariance matrix. So you get this Z, you take this Z, you send it to the decoder, and the rest is more or less same. The decoder now generates your image back. Okay. So here, I mean, it is also assumed that your image space is also Gaussian. Okay. So the decoder, essentially what you are trying to do is, you are initially in the encoder stage, you are trying to model this distribution. You're trying to learn this distribution q of phi given of z given x. So given x, you are trying to model a distribution, the distribution of z. That is the encoder side. Decoder side, you are just doing the opposite through another network parameterized by theta. So given z, you are trying to learn the distribution of x. So it's just the opposite. So again, it's basically, again the assumption is that this is also a Gaussian with some mean mu x and some covariance sigma x. So you make the decoder predict these two. Again, just like the encoder, you just make the decoder predict these two, mean and covariance. So you get the all the details for the Gaussian. So now you have control over the Gaussian and just sample a new image from here, right? So that gives rise to your new image. And the normal, so in autoencoders or variational autoencoders, this loss is actually pretty simple. So what you want is that whatever image you have started with and whatever image that you are getting at the end, this particular x hat, they should not be very far from each other. So that is the idea. So how do you ensure that this x and x hat aren't very far? All you have to do is have a MSE loss like this, which will kind of ensure that your pixel values in x hat are not very different from x, the original one, right? So this is like x hat minus x and square of 2 now. So this is the okay. So this is, I think, this is written in the opposite way. So this is going to be the generated image. This is going to be the true image. So that is what you want to keep in mind. So this was, again, this was enough for variation, sorry, for autoencoders where you did not have any restrictions on the latent dimension z, latent vector z. Now, in the variational autoencoders, you have put a restriction. Remember that this z has to be sampled from a Gaussian. This z is not like any vector in the vector space. It has to be sampled from a Gaussian with a certain mean and variance, right? So that is why this elbow lower bound um, came into existence, which says that your you do not only need to have this reconstruction error. So this reconstruction error again is what, that you have an input x hat and sorry, you have an input x and your generated input is x hat, and you are trying to make them as similar as possible. Similarly, there is a KL divergence loss as well. So again, repetition. So KL divergence is used to compare two probability distributions, and the lower the value of the scale divergence, that would indicate that the distributions are more similar, right? So this posterior distribution, so this, you can see that this QZ given X is a posterior, and you are saying that this posterior distribution should be uh, you know uh, similar to your prior distribution. So prior, it's thought of as so prior distribution is taken to be this P of z is a Gaussian distribution with mean 0, and some the covariance is taken to be the identity matrix I. So what you would want is these two distributions to be very, very close. So that error is also kept. So in order to make sure that your z is actually sampled from a Gaussian. So you are inherently, through this second part, you are trying to make q of z given x match this p of z. So posterior is trying to be matched up with the prior, and the prior is taken to be the prior of z. So p of z is taken to be a Gaussian with mean 0 and covariance as identity. So these are more or less the two loss functions that are used in variational autoencoders. So now, yeah, finally I found a question where there is no answer. So who will answer this question? Someone please take the responsibility, and this is actually a very simple question. Uh, Please go ahead and answer this. When nobody is trying, is it? Fine. Let me go through it then. So see, if you are given the average of the latent vectors corresponding to men with hat, okay, men with hat is given by this latent vector v1, men without hat is given by this latent vector v2, and women with glasses is given by this latent vector v3. Okay, so which of the following is the most probable generated images with the latent vector v1 minus v2 plus v3? Okay, so you can think of this information, men with hat, as something like men plus hat.
Absolutely.
Yeah,
But is it women with hat and glasses?
yeah, correct, correct, you are correct. So can you explain why?
So in the first vector, we have men with hat, and in the second
Right.
vector we have men without hat. So when you subtract
Hmm.
that both, men gets subtracted. So we just
Correct,
have hat. And
correct,
in the third vector we have women with glasses.
correct,
So if there's no men, there should be women
correct,
plus hat plus
correct.
glasses.
Right. You are absolutely right. So your the answer becomes woman with hat without sorry, with glasses. Woman with hat and glasses, the fourth option. So again, just to clarify what she said that absolutely right. Her answer was absolutely right. So you have a vector representing men with hat, and you have another one representing men without hat. So when you subtract this from this, what remains is your hat. Your men gets cut. Your men gets subtracted, and so it's non-existent. So all you are left with is hat from these first two expressions, and then you add women with glasses. So you add women with glasses with hat, and that basically adds up to this woman with hat and glasses. Simple. Okay. So now next question, in a VAE, if the encoder outputs mu equal to this, so this is a three-dimensional Gaussian, and sigma equal to this, and you have a some epsilon sampled from N01, N0I basically. So that epsilon is given by this quantity. So very often, okay, so let's read the question once. Then the latent value z given to the decoder is what? Okay, before going into it, so let's revisit the picture once again for the variational autoencoder. Okay, so here what we have said is that the encoder is generating your mu and sigma, and so you get hold of the Gaussian, and you get a this you can sample this z, right? So very often what happens is, instead of doing this directly, you will be instead of sampling z from here, you may be what you may do is, you may sample some epsilon from a normal distribution from another Gaussian with zero mean and unit variance. So once you have that, the way to so the question is about, then once you do something like that, how do you, so you have this mu, you have this sigma, and you have that epsilon which is generated from a Gaussian 0 1. So 0 and unit variance. So how do you generate this z back from that sort of an information? That is what the question is about. So it's actually going to be something like this. So we all kind of have an idea about it, that so given something like this, all you have to do is so when you are given this mu sigma and some value generate some vector generated from zero mean and unit standard deviation Gaussian, so that translates to something like this when you combine them. So it's mu plus sigma times epsilon. Okay, so mu is given here, sigma is given to you, epsilon is given to you. So all you have to do is just feed those values in this formula and you get this, right? So you have been given this mu here, sigma is given, and what your sampled value is going to be is mu plus epsilon times sigma. Okay, so if you don't get it, revise your Gaussian lessons once again, but this is how it is going to be. So it's a very simple question which is kind of just asking you, how do you sample your Z if you are given values in this way, right? So this is simple. Okay. And the last thing in theory today is so GANs and VAEs have a notorious habit of failing under certain circumstances. And note that this from what I've seen, this is not a solved problem yet. So various researches are going on arresting this failure. So what happens is that, suppose you have a multimodal distribution like this. So you have multi modes in this. So your this dark blue basically represents your true data distribution as shown here, and it has these two modes, or it can have even more modes. Okay, so VAE, if you try to fit a VAE here, the VAE will be the approximate distribution generated by the VAE will be something like this, which is totally dissimilar uh, from the actual true data distribution. And GANs, what they'll do is, GANs will tend to fit one of the modes. Okay, so it will try to fit something like this inside one of, so approximate this mode but not this mode, it leaves this mode alone. Okay, so GANs generally tend to ignore the other mode, and this problem is known as mode collapse. So what happens is, when mode collapse happens, when you have learnt an approximate distribution that only models one of the modes, you keep on generating almost same images every time. So when you generate images, the expectation is that, suppose you are generating flowers, okay, expectation is that you generate different flowers which look a little bit different, colors are different, and so on. So every flower image will be different from the other in some way or the other. But when this mode collapse sort of thing happens, then because it has learnt a distribution in this way, uh, so then what happens is, your GAN kind of always generates the same flower with very, very minute or zero difference between two successive generated images. Okay, so that is one of the problems of GAN, and again research is still going on in this area in order to avoid mode collapse and how to design GANs which which can fit multiple modes of the true distribution. Yeah, there has been some success and still some research is going on in this area. Right, so more or less the theory part is done. So the more fun practical part will be done now. So today we have autoencoders. Um, so yeah, so let's start with that in the code. Let me increase the font a little bit. Yeah, yeah. So please go through these writings because yeah, you'll get a lot of explanations about motivation behind autoencoders and all. So as I said, like one motivation is that behind autoencoder is that you would want oops, yeah, what you want is you have a huge image which consists of many pixels, and you want a representation of that image in a much lower dimension. And it has been seen that so where let me see, I saw it somewhere here. Mm, yeah, so if you look at this particular sentence, real world high dimensional data actually consists of low dimensional data that is embedded in the high dimensional space. So that is why they are saying that even though your data might have huge number of dimensions, it can be compactly, the information that is there in your data can be compactly represented in a much lower dimension. So that is why these autoencoders, ECA, all these concepts have come up to ensure this sort of a to ensure that this we can represent our image through much lower dimensional feature space. So right, so let's dive into autoencoders. So autoencoders, if you let's ignore this part, yeah, the image I think is self-explanatory. So you have an image like this. So images are generally 3D or 2D in structure. You have flattened them into a vector, right? And now what you want is you want a neural network to learn something. There should be a neural network which maps this high dimensional data to some low dimensional data. Okay, something like this. Okay, so approximate that neural network by the small e. Okay, so given an x, this small e generates your z. So this z dimension is much smaller than x dimension. Okay, and how do you train this sort of a z? What you can do is you have, I mean, you learn z in such a way that, so as I said a few seconds ago, that the information that is contained in this z, in this x, is somehow we want that to be compactly present in this z. Okay, and if that is true, then given your smaller z, you can again reconstruct your x back. Okay, so that is given by this pink part. So given this z, you again have a neural network which goes from this, which maps this z to some x hat, which is supposed to be similar to your original x. Okay, so this is the encoder, this is the decoder given by E and D, and obviously z equal to E of x, x hat equal to D of z. And very simply, what you would want is that these two should be as similar as possible. That is why you have that uh, you keep losses like MSE and all. So this is your original image, this is your generated image, and these should be as close as possible. Okay, so let's start running. These are yeah, these are simple things. Okay. Okay, so let's look at the keep looking at the code. So encoder instead of yeah. So what is an encoder comprising of? So encoder is probably something like here they have taken it to be a two hidden layer neural network. Okay, so suppose you have an MNIST sort of data set. So let's run this one. you have an MNIST sort of data set. So you know that MNIST is 28 cross 28, which amounts to the 784. To this 784, you have attached a 512 layer, hidden layer through this nn dot linear, and again you have another 512 you have another hidden layer which is a dimension, this latent dims. So this is going to create your final hidden vector z. So the idea, the forward function is something like this, that you first flatten your image. This x was some 2D or 3D image, you flatten it, and then you pass it through this linear self dot linear 1, pass it through this ReLU as expected, and then pass it through the linear 2. That gives you a vector from, so starting from x, that gives you a vector of dimension latent dims, right? And now what the decoder does, again it's very simple. So it's just the opposite, right? So you start with latent dims, go to 512. This 512 is a hyperparameter, you can change it if you want, but obviously, yeah. So this yeah, so you go from this latent dims to 512 and then from 512 to 784, right? And so this is how you define the forward function, that you start with z, you do a you pass it through linear 1 which converts z to 512 dimensional vector, pass it through ReLU, and then you again pass the resultant vector through this linear 2 which converts the 512 to 784. So now at the end you have a 784 dimensional vector. And now what you want is, since your image is it is the pixel values we have taken to be starting, I mean in the range 0 to 1, that is why you have a torch.sigmoid outside which basically compresses the values that are output by this linear 2 to values between 0 and 1. And now you reshape it to your 28 cross 28 um, image shape, original image shape. This kind of gives you your reconstructed image. Okay, right. So now your autoencoder finally. So you defined your encoder, you defined your decoder. So that is so in the autoencoder class you have these two in that way. So it's very simple. You generate from, you take x, pass it through encoder, generate z, and then from z you pass it through the decoder to generate your image, generate your image back. Okay, now this is the training function. So again the idea is that mm, you pass your input image through this autoencoder and automatically get back this x hat, right? And now your loss is what I told you, that you have the original image, you have the generated image, and you do a square distance. You find the square distance between these two and you try to minimize that, right? So this is the simple train function, right? So this is some code which basically generates the MNIST data. I believe you have seen it multiple times. So let's move on from here. So yeah, so this particular, so once you have been able to, okay, where are they? Oh, okay, okay. So in this particular block, you are not only downloading the MNIST data, you are also training the autoencoder. So everything is happening automatically. But now what the interesting thing that we want to observe is that, so now you have learnt your Z, all right? So now you want to see, like, in the Z space, what do the different images look like. So this is like, since I've shown you that the input image data set is MNIST, we all know that MNIST is nothing but handwritten digits. So the input data start from 0 to 9. Okay, so we inherently know that your data has these 10 digits. Okay, and now that is why they wanted to kind of see, like, let's not run it because already the training is happening, but yeah, they wanted to see, like, for example, if you look at all the z's, all the z's, then I mean, where does one map? If your input image is 1, where does 1 map on this space? Where does 9 map on this space? Where does 2 map on this space, and so on? So let me reduce this a little bit more. Okay. Yeah. So you can see that this is how it looks like. Okay. So you start with the image, you know what class it belongs to, and that is how they have generated the colors. Okay. And you see basically if you just plot the z's. So here I think if I'm not wrong, yeah. Here, the good thing about this is that they have taken this latent dimension to be 2. So already your z is kind of two-dimensional, which is why you can directly plot this. So you see that there are different islands. So the 0 corresponds to this particular one. The 7 corresponds to this one. 1 corresponds to this one, and so on. So more or less, I mean, these are, so you can see that there are clusters, but all of them are not very well separated, that is true. And they are, I mean, some of them are spreading a lot. So those problems are there, but you still get some islands, or I mean some clusters from each of the digits. That is good. And also there is this so this is how the generated images look like. Okay. So yes. So this is how you are generating the images, and you are traversing through the latent space basically, and this is how your images look like. But you will notice that while some of them are good natured, so you can understand these seven. So the seven started turning into nine here. So this is like four and between 4 and 9 something. So these are still not very distinct. Okay. So in order to to make them better, we'll go into variational autoencoders. So what are variational autoencoders? They are something like this, that what I said right now. So you have this input image x. A neural network basically learns your mu, and your this is going to be sigma. So your mu and sigma is being learnt by a neural network. You just sample your z from the Gaussian, resultant Gaussian, and from z you basically decode back your image. Okay. And yeah, so this is how your, this is the elbow thing that I talked about, the KL divergence loss, which is simplified to this particular value. So let's have a look at the I mean just a short look at the code. It is very similar to the previous case, just that now you have a so you have these three linear layers. So one is mapping from 784 to 512, that is fine. The other two are same basically. So they are just two different weights going to the same dimension, 512 to latent dims, both of them. So then you have a normal distribution 0 comma 1 and so on. So what happens here in short is that you flatten your input, you pass it through your this linear one, which transforms your 784 to 512. Then you get your mu through the first, I mean this linear 2 that is there. Let me increase it once again. Yeah, you pass it through linear 2 to get the mu, and you pass it through linear 3 to get the sigma. Okay. And now just like we showed in the problem there, you instead of sampling from mu sigma, you basically take a sample out of this normal 0 comma 1, 0 comma this unit Gaussian basically, and you do this sigma into sorry, mu plus sigma into this epsilon, which is this sample from this unit Gaussian, and you calculate the KL divergence as described above based on this equation. So that is your variational encoder. So just note one thing, that variational encoder is the only thing that is different from autoencoders encoder. Decoders can be still used in the same way. So uh, to define the class, it's like this, that you in the encoder you put this variational autoencoder, and the decoder is like the previous decoder. Okay. And this is again the same thing, that you generate from x you generate z, from z you generate x again. Okay. So here in the training function, what you see is again what I said, that there is this you do this MSE sort of loss, this squared distance loss, that is going to be first, and then you have the KL divergence loss to make sure that your posterior is close to the prior, right? And then the only thing that last thing that I wanted to show you is this particular plot where yeah, so this is actually generated for this is the latent space of the variational autoencoder, where you see that the clusters have become much more compact and they are looking somewhat, if you look up you'll see that they are looking somewhat, more distinguishable than before. So this 0 represents this one, so 1 represents this orange, so you can see the others as well. So right, so here I mean they have also explained the difference. So we can see that compared to the traditional autoencoder, the range of values for latent vectors is much smaller and more centralized. Okay, the distribution overall of P of z given x appears to be much more closer to a Gaussian distribution. Okay, so now you can clearly see that these images, generated images, are kind of much in some sense they are quite clearer than the previous case. So yeah, so variational autoencoders produce a latent space Z that is more compact and smooth than that learned by traditional autoencoders. This lets us randomly sample points Z from some space Z, capital Z, and produce corresponding reconstructions that form realistic digits unlike traditional. Right. So this is more or less about today. So I have to leave now. I have a meeting. So let's call it a day. Yeah, and I hope you enjoyed this entire week of generative models, and so GANs and variational autoencoders. They are pretty interesting, and lot of research is going on. As I said, go back and look at the papers that are out there. So I'm sure you'll find them to be very interesting.
Thank you, ma'am. Thank you very
Thank
much.
you. Okay.